we are going to be taking a look at entanglement. Yeah, I've been trying to be like banging my head against like this whole thing of modeling entanglement for all this other stuff that I was building in the simulator, but I kind of realized that I'm sort of a beat stack, so I'm maybe I should just kind of go back one step and just take a look at entanglement from other perspectives as well. And 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 yeah, wait a second, is the mic getting the right sound? Yeah, okay, cool. And there's still one piece that I didn't fully understand when we went through the technical introduction, which was the entanglement part, and I want to kind of revisit that because I there's a consequent mechanics. Um, Entanglement. There was entanglement in Wolfram physics project. There was somewhere where they did say that. Yeah, I should probably watch these videos and actually do some commenting on these. Definitely. Wolfram Cloud. Oh, what is that? Some quantum mechanical properties of the Wolfram model. So this is an introduction. Insanity principle. Okay, that's way more detailed. Entanglement-like or branch-like? Mm. Entanglement cone in the multi graph, which by proving the entanglement structure of the multi-way system allows one effectively to determine the maximum theoretical rate of entanglement between global multi-way states. I'm looking for something a bit more entry point. It's not in here. Maybe it's in the formalism. Yeah. A part feature is entanglement. Connection or correlation between states. In our setup, as we will see more formally, so entanglement is basically a reflection of common ancestry of states in the multi-way graph. Interference can then be seen as a reflection of merging. I so I know where this is going, right? So I think what one of my intuitions is telling me that what this means is because this is the multi-way graph and this shows the evolution of a system, what you're saying is that, for example, these three states are entangled because they have the same ancestor, and so they evolved out of that, and they didn't get merged, right? So, but again, but again, each but again, each of these things is supposed to be each of these things is supposed to be a basis state. That's what I remember. which is a bit hard to map to some concrete quantum computing example. That's what I'm trying to find, maybe. Each pair of states generated by branching in this graph are considered to be entangled, and when the graph is viewed as defining a rewrite system, these pairs of states can also be said to form a branch pair. So given a particular foliation of the multigraph, we can now capture the entanglement of states in each slice of the foliation by forming a branchial graph in which we connect the states in each branch pair for the string substitution system above. Like what's confusing a lot is that they talk about entanglement about states, right? Which is essentially different than the way that I'm trying to model it, which is like because they talk about system states and I talk about qubit states, and that's what it's really hard for me to understand from a quantum mechanical perspective. What is it that it's entangled? I always thought it's the subsystems that are entangled, right? Not the states per se. Mm, mm. Like entanglement kind of is a type of correlation that is defined as in the sense in which we observe correlations in the measurements um, of different systems, right? So that's what confuses me of the usage of the word entanglement in here, especially because I still can't understand how this is mapped to basis states, right? So each state in the multi-way system has some quantum basis state S. That's what it says here, quantum basis state. That's what I think this is getting wrong, is that it's effectively a phenomenon of connection or correlation between states. I mean, in a way, it is, right? Because that's what that's also what I thought the density matrix actually tells you, right? Is sort of the correlations between different pairs of states. But it's not necessarily a correlation. Like for me, a correlation is you're observing two independent things, right? And you can see that these things somewhat have a relationship, right? But I can't. Let's put it this way: if I have a system and I start in the state 0 and I apply the Harmar gate, then I can be either in the state 0 or 1, right? That is not entangled. That's I mean it's two basis states, and so I'd say you would see two different legs in here, right? But they wouldn't be entangled like that. That's there is a correlation. There is a correlation in this in the sense that there is a certain probability of measuring one of these basis states, and if you know this one, then you know the other one. Yeah, maybe that's the correlation, right? In a sense, that's what a density matrix would tell you, right? There's a definition of motivation. It's a linear operator called a density operator. Density matrix obtained by density operator by choice of basis. So it is important to emphasize the difference between a probabilistic mixture of quantum states and their superposition. If a physical system is prepared to be either in the state um, uh, psi1, psi2 with equal probability, it can be described with this mixed state. So essentially, yeah, and the superposition is these, right? So the difference is these non-diagonal, as in like non-fundamental diagonal elements. Um, and you could read these. So if this is the probability of measuring 0 and the probability of measuring 1, right? Like so 1/2 and 1/2, this is then something that relates these two probabilities or these two basis states, which is 0 because it's a mixed state. Whereas in this case, there is a half, which basically tell you the what does this tell you? It tells you I mean, what does this tell you, right? It it tells you something about it tells you something about the fact that you're not in just the one state or the 0 state, right? Is that you're in this sort of state where it's kind of a linear combination, right? So that one would tell you, that 0 is telling you that there's no correlation between the 0 state and the 1 state, whereas here it tells you that there's a correlation. Now, I wouldn't go that far to call it entanglement. That's what I think it's misleading here. Because essentially that's what I imagine these doing, right? So it's saying, I applied Hadamard gate here, and so I go to two branches, the 0 and the 1. Still, that's just not entangled, right? That's confusing. Should play maybe with this model a little bit more, but I don't know how to do this. So I'm convinced this is just, it's just a naming. Hangman. Where's these? Tensor matrices. Hmm. So, hmm. Hmm. I was just entanglement, man. So quantum entanglement is a physical phenomenon that occurs when a group of particles are generated, interact, or share spatial proximity in a way such that the quantum state of each particle of the group cannot be described independently of the state of the others, including when the particles are separated by a large distance. The topic of quantum entanglement is at the heart of the disparity between classical quantum physics. So measurements of physical properties such as position, momentum, spin, and polarization on performed on entangled particles can in some cases be found to be perfectly correlated. For example, if a pair of entangled particles is generated such that their total spin is known to be zero, and one particle is found to have clockwise spin on a first axis, then the spin of the other particle measured on the same axis is found to be counterclockwise. So this behavior gives rise to seemingly paradoxical effects. Concept, non-locality. Entanglement as a resource. Like, I know all this stuff, I think. I just, because I had the hope that these some sort of would kind of enlighten me a little bit more in terms of how to model entanglement um, for ANSYS in a way that if this is how it's defined, right, what one could imagine that that is the point, right, of if you keep track of the evolution, then you know when things are entangled and when not, which is kind of true. It's kind of where I'm at the moment, and I'll make an update soon, I guess. But it's just uh that bothers me. There's no I've got a system of, say, 2 qubits, right? For me, the entanglement, or 3 qubits, for me, the entanglement in here, it's sort of a notion that is based on, and it's built on these kind of components. Like, how are these 3 elements um, entangled or correlated? Because what is it then so special about the density matrix of, let's say, let's just take two qubits, right? And compare. Okay, this and take the density matrix. So it's basically this one, so, right? So what you're saying is the coupling of 0, 0 to 1, 1. There's a coupling between these two, right? Whereas if I do these, you know, there's still a coupling between these two, but there's also a coupling between everything else. Sorry, there you go. Are there, so let's try another one. Let's say, for example, that I now do these, right? That is entangled. So there's still couplings between everything else, but then these couplings have different. So how can you tell? The couplings don't tell you whether you're entangled or not. Like, and in this and in this particular case, in this particular case, right? Maybe I should just maybe I'll do that. Like maybe I just needed something concrete. I feel I'm a bit lost. So I will just what I will do is what if I do like the JS Paint app thing? So yeah. So where am I? There am I. If I start the system, if I start at the zero state and then no the 0, 0 state, right? Because it's a two qubit system. Then I apply sort of the Hadamard in one qubit and the other qubit. So let's just go one operation by operation, right? So the first Hadamard would basically take me to the 0, 1 state or to the 1, 0 state. In Wolfram, this is Wolfram's, right? So that's what I'm trying to do. No, what the fuck did I just do? Oh no, that was correct. This is not correct. So I'm applying the Hadamard in the first qubit. And so I'm saying, it's either this state or this state. Right now I'm applying the Hadamard in the second qubit. And so I have 0, 1 state or 0, 0 state. And here I have, of course, the 0, 0 state, right? No. This is first qubit, this is second qubit. Let me just do this in order. This makes more sense. So stays the same. Now we're doing the second qubit and goes to 1. And this one basically stays the same or goes to 1, right? So this is, this is the way that I think about this, right? How the multi-way evolution graph will look like. Now I do a control Z on these. So we're doing this case here. Now I do control Z on these. Control on, say, the leftmost qubit. So this one evolves into 0, 0. This one evolves into 0, 1. This one evolves into 1, 0. And this one, right, evolves into so how did I do that? I don't think that's correct. No, that is correct. It's supposed to be a basis state, right? But how do I? Okay, so the thing is, it cannot be. And maybe I'm just too hooked up with this definition. Is effectively each state in a multi-way system as some quantum basis state. Because that would be like, I don't know where the amplitude would be stored in here, right? Because now, like, that's all fine, but like if this is a basis state, like where's the, where's the amplitude stored? Is it it can be implicit, right? Because now I would say, minus 1 1, right? And that is kind of what makes the qubits entangled, right? Because I just have to find, I want to find a better example. Like, I want to find a better example. And maybe, so, mm, 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 mm. I want to find an actual quantum computing example. Project K software tools. Working material archives. Oh God, okay. 1994. Okay. mm. Okay, that's the one I found. And then this is a tools introduction. Archives of working sessions. Oh, look at this. Maybe in the notebooks I can find something. So here's all the notebooks. So let's see, what if I search quantum computing? Because I want to find a specific example. Cones. Here is always a time unit, light cone. Projection of cone into spatial graph is CT, branch cone, quantum branch cone, rule cone, Hilbert space, quantum amplitudes. To get from one quantum state to another requires follows branches on multi-way system. Linearity from combining paths. Okay, I think the reason I'm getting confused in here is because this might be somewhat closer to the path integral stuff than I might have anticipated. Linearity comes from combining paths. Actual bracket requires projecting from one set of states to another, approximated by distance on the branchial state graph. quantum computing. We have non-determinism in the sense of NDTMs, but not in the sense of randomness. Does this mean we can solve any problems? No, because of causal invariance. There's a trade-off between objective reality in QM and the ability to do NP computations. What is the difference between NP and confidence systems? Live stream archives. So so there's a bunch of working sessions exploring quantum computing. Or no, that's one actually. Oh, that's an actual one session. Because I've watched this one, I think. So what if I cannot search here, I guess. Oh, that actually goes to that moment in the video.
So if we say state association, I guess that's the key thing, right? So internally, what this measurement is an association mapping names of the measurement outcomes onto QDSs. Some of which will be pure. Some
I
of which
can't
will be
hear the
mixed
video.
in general.
That's the thing.
And so it's these quantum discrete states that are the actual measurement outcomes.
It's because of how this is
this
routed.
ket notation is just a way of denoting which QDSs were measured. So in fact, what we really want to do is not say simulated measurement, but simulated state measurement. And okay, this
oh yeah, I see now messages in chat. Oh, that's you, Victoria. Hi.
Oh, sorry, it's misspelled
yeah,
So we get a collection of quantum discrete states that are the outcomes
probabilities.
Okay, but so I don't quite understand why the keys in the measured results.
See more. Quantum observers and NP completeness. More examples of multi-way systems. This is quite complicated to navigate past the introduction stuff. Okay, so we have a bunch of other results here. Entanglement horizon, spaces, quantum spaces. Let's take a look at this. This looks a bit promising. Maybe less. For example, A, B, multi-way system, causal graph, branchial graph. Okay, entanglement definitions. Look at this. So tensor product states not interacting in multi-way system. No correlation between directions. Oh, you mean these two things here? Substitution system causal graph. Multi-way action distance multi-way causal graph. There can be connections between spatially distant events. Path integral state is just the state vector. Weighting of the state, amplitude is the measure, and the multi-way geodesic bundle. State vectors are local to branch-like hypersurfaces. States have particular coordinate positions in multi-way space. If there's no entanglement interference, the multi-way causal graph will be a direct product of individual causal graphs. Okay, so here they yeah, but again, that's like entanglement, common ancestry. Fuck, man, that's confusing me. I want an actual example. Spaces, weighted multi-way systems, okay. The following gives the relative weightings of edges emanating from a node. Directive large. Okay, so this is basically saying that you've got multiple edges and so you sum them up. Okay, 1, 1/2, 1/2, 6 1/2, 1/3. Yeah, those are weightings, but we need complex numbers here, right? But okay. Counts. It's all cool. States graph. Branchial graph. Each node is a ray in Hilbert space. The weight is the norm of the state. The direction of the state is determined by edges. What is the interpretation of distance in branchial space? Insofar as ancestry distance, entanglement distance. In the Hilbert space, we have elements A and B. They are represented by complex numbers. We know their norms. Each node carries an amplitude. So each node carries an amplitude together with entanglement information with other nodes. What? The magnitude squared of the amplitude is the path weight of the branchial node. We might want to know the scalar product of a node with another node. For this, we need direction info as well as magnitude. Unitarity is guaranteed by path counting, and then we normalize. The Hamiltonian is a transformation from one branchial graph to the next. From one branchial graph. What? An operator represents that an event that one does which changes the branchial graph. Yeah. Tending event. Because some nodes kind of make sense, but others they just don't make sense at all. To me, I mean, and I'm just probably not understanding this, but they're playing with weights in here. So in a way, right? Like one could say, look, if I have my, let's say I have two systems, one that evolves like this, right? And so these nodes have weights. I almost kind of like, almost think the way that I was modeling it before with ANSYS was actually the correct one, where we have nodes are states, right? It's just they, and it's funny because I think what the Wolfram model does is it tries to model entanglement with the sort of kind of keep it like keeping track of the evolution. That's so like the thing with the ancestry just doesn't feel right, but doesn't feel wrong either. But so this would be, this is kind of the updating event of applying a Hadamard gate, and then you've got another qubit that you kind of do the same, right? And so essentially, if you do the product of these graphs, right? Like you actually, I I don't know how the how you do the product about these, but I guess you kind of you multiply each edge by each edge, right? So you're saying, yeah, essentially, probably that's what you do. Like, is there a definition of a hypergraph product? Probably many. And what is a graph product? Yeah, modular product of graphs. Yeah. Okay, so this one, right? So if you have oh, that's Mathematica. That's why this thing seemed familiar. But essentially, I guess what I'm saying is, if you, or what this seems to indicate is what I, yeah, so basically you do these times these, so you have, So you see, you basically have the product of all of these stuff, right? It's just that um, hmm. you but something's not correct because you wouldn't want to multiply this one with this one, right? How would you go about connecting these? That makes kind of, it's modular product of graphs. That's not what we want. Here it said something else about product. Product. Inner product is the dot product of the vectors attached to different nodes. Each vertex has a vector. So you'd kind of say, I mean, the way that I imagined that, right, is, yeah, you kind of like have that, right, and then you have basically, these multiplied by these and these multiplied by these, right? So you kind of have, yeah, you'd have these, so, and then you'd have these, and then you have these, and so that's kind of the, but that means they're separable, but like still, like that wouldn't tell you, right? Some of these nodes, they're just a bit confusing because they seem to contradict each other. Quantum. Maximum entanglement rate. They also talk about entanglement speed. What is entanglement horizon? What is a black hole? Split in a causal graph. Sorry for foliations. I have just absolutely no idea. This is these notebooks are cool, but they just lack a lot of context. So definitions, 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 definitions. It just makes it complicated. This is complicated to navigate past the technical introduction. So you've got this kind of stuff, and then relativity and quantum mechanics. I don't know. To be honest, I still think that's not, that's, I still think that's not what is, you know, yeah, that's not what, that's not the way that I expected Entangled to be modeled in here. That's, to me, that acts a bit like the density matrices coefficient. So it yeah, it does show some sort of couplings, right? Because or you know, in a way you can call them correlations, but they are not the entanglement correlations that you, the way that you typically be introduced to them. I don't know. I need to think about these. What do I want to do next? How do I want to move forward? I want to learn more about entanglement. I've read some stuff about quantum discord recently, which was quite interesting, right? In terms of the entanglement just being like a thing of the pure states, right? But if you think about mixed states, and there's also other correlations in the in a mixed state setup, where some correlations also do appear, which are not necessarily entanglement. Entanglement is just a thing of pure states, but I think we can just stay in pure state land for now. And yeah, kind of as I try to figure these out, I need to find a way to move forward with the project, or at least with the idea of learning more about quantum mechanics, because that's what I set out to do, and I got a bit distracted with the whole entanglement modeling thing, which I want to keep pushing, but I'm like, how could I understand these? How could I understand these better? Quantum formalism. Maybe I should kind of entanglement and the path integral, right? Over entangled states. Okay, look at this. There's some video. This seems to be like, oh, look at this. because the Wolfram model seems to be connected to that somehow, and that to the path integral formalism. Can path integrals be used to understand entanglement? I like path integrals. I prefer to try to understand quantum phenomena in terms of path integrals rather than Hamiltonian mechanics. However, most of the standard text, this makes it feasible for me to gain insights into common phenomena, with a few exceptions like certain areas of optics from the perspective of path integral formulations. I'm aware of some exceptions. Blah, 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 blah. So path integrals have been used to discuss entanglement in quantum fields. The path integral is used to trace out part of the system, so that the entanglement is given in terms of von Neumann and entropy in terms of the trace of the partial density matrix. You can find an example here, for instance. Common entropy on an area. God, that seems complicated. I'll watch this video maybe. And then kind of comment on these. Path integral approach entanglement and non-equilibrium dynamics.
Integral approach.
That just might be too
But
dense.
once you try to look at is this.
I need to understand the path integral stuff a bit more. Yeah, let's do that. That probably seems like the best way forward. Sort of try to understand more about the path integral and then try to understand how can we describe entanglement with a path integral. That should maybe help me understand and gain more insights into the whole entanglement stuff. Gotta go now. Bye-bye.